This Mario Kart here is not driven by a human. It's driven by a machine learning model. And that machine learning model is not driving it on an emulator, but on a real physical Nintendo 64. And it's actually quite good at driving. In this video I will show you how it works, how I trained it, and also what you need to reproduce it. As many others, I've got a casual interest for machine learning. I've dabbled around with TensorFlow and created a couple of simple classifiers. However, recently I wondered how difficult it is to use something like TensorFlow to control something in real time. And what better target to use than one of the first console racing games I ever played, Mario Kart 64. My plan was simple: get the video output from the N64 to my computer, do the calculations there, and then send back the required controller inputs to the N64. Now, getting the video output was pretty simple. I connected the N64 to an AV to HDMI adapter I had laying around and hooked that HDMI output up to an Elgato HDMI capture card. For getting the controller signal from the computer to the N64, I had to get a bit more creative. I couldn't find anything ready to use, so I built my own adapter using, you guessed it, a Raspberry Pi Pico and the cable of an old broken third-party controller I had laying around. The programmable I/O features of the Pico came in really handy here. You can find the source linked in the description. With everything hooked up, I had this setup: my N64, the AV adapter, the capture card, the laptop, and the Pico. I also hooked up a small monitor to the capture card pass-through to be able to see what's going on without having to render it on the computer. Time to look at the software side of things. When I started this project, I started looking for others who tried the same. And pretty much immediately, I found an awesome project by Kevin Hughes called TensorKart. TensorKart is a machine learning model and toolset for controlling Mario Kart 64 on an emulator. It uses a specially modified version of Mupin 64 Plus so that it can basically single-step frame for frame and send joystick inputs for each frame. While I did not want to use an emulator, mainly because I was interested in the challenges that come with doing all of this on real hardware, I decided to use TensorKart without the emulator part as a base. The code of TensorKart is beautifully simple and comes with a training pipeline that is easily adjustable for what I wanted to do. What's also really nice is that TensorKart is based on a network from an NVIDIA paper that is actually able to control real cars, and so I was super excited to see whether I could get it working on a physical Nintendo 64. With all that in place, let's talk about training data. My goal was to create a supervised model. This means that to train the model, I want to give the model what's called labeled training data. In this case, the input to the model is a frame of the game, and the expected output of the model is a steering input, aka the label for the training frame. Now, to successfully train a good model, I need thousands of frames of the game and the correlated steering input. To generate this type of data, I first wrote a small Python script that takes the input of a connected gamepad, in this case a PS4 controller, and sends it via my Pico-based adapter to the N64. Combined with the HDMI capture card and a modified script from TensorKart, I'm able to capture frames from the N64 on my computer and capture my steering inputs for that frame. Now, as you can see here, the whole signal chain has a ton of lag. From my controller, through my computer, through the USB adapter to the N64, and then back through the AV converter into the capture card and to the screen, I've got like a second of lag or so. I optimized the Pico code a bit more to make it a bit better, but in the end I just hope that the lag is not too bad and that it's good enough to train my model. With this setup, I started recording training data. Now, a big issue is that when you play Mario Kart 64, your inputs normally are not particularly smooth. You tend to have very harsh steering inputs. This does not train well on the machine learning model and will create quite a bad model, especially without reinforcement learning. To make it easier to have smooth steering inputs, I reduced the maximum steering angle in my controller script, and I decided to also start training with basically cruise control. I set the gas button to be pressed for 500 milliseconds and then released for 500 milliseconds automatically, so that the car always drives at more or less the same slow speed. Using this, I drove 7 full-time trial runs of Luigi's Raceway, trying to steer as smoothly as possible, and ended up with over 10,000 frames of data. And with this training set, it was time to train the model. Well, almost. In reality, I spent a ton of time trying different training approaches, models, fixing bugs, and so on. And so what looks easy in this video actually took a lot of time and experimentation. I also modified the output shape of the model. Instead of outputting gas, brake, and joystick X and Y, I wanted the model to only output a steering signal. And with all those things set up, let's train the network. I started out with 200 epochs, and as mentioned, we are training on a very slow-driven dataset. The training is really fast on a decent GPU, taking less than a second per epoch. On a CPU, however, this will take much longer. With the training done, we can look at our loss, which describes the difference between the output of the network and the labeled training data. As you can see, it looks like our training performed really well. Both loss and the validation loss, which is the loss of the network tested on data that it wasn't trained with, is going down a lot, and more importantly, the validation loss stays low. This indicates that we are not overfitting. Overfitting is when the network learns to recognize the training data instead of actually learning to drive. So, time to give this model a try on the actual hardware. I modified the script that normally controls the emulator to capture frames from the capture card, run them through the neural network, and then send the joystick input via USB to the N64. For the first tries, I used the cruise control again, making the testing annoyingly slow, but you have to walk before you can run. As you can see, it already tries to do something, but it's not really driving well yet. It's steering in the right direction, but the steering inputs are too harsh and it always lands in the sand. But definitely a great base. After a lot more debugging and changing different model parameters, I eventually got it to the point where it drove, in slow mode, 3 full rounds of Luigi's Raceway, without bonking against any wall and without driving into the sand. One of the most interesting things that I noticed was that the network seemed to learn from the HUD. If I had the map enabled, it seemed like it would primarily learn from the map. Disabling the map and cropping out the HUD parts, such as the timing display, drastically improved the model's performance. With that working, it was time to create some additional training data, this time driven at full speed. I also added 2 rounds of Calamari Desert to the training data, in the hope that it would help the network to learn to generalize better. And with that, it was time to train again. And what was really cool was seeing how with each increase in epochs, the model got better and better. After 10 epochs, the model would start steering in the right direction, but always bonk against the sidewall. At 20 epochs, the entry to the curve was quite good, but then it would steer outwards, bonk against the outwall and land in the sand. At 50 epochs, the first curve was no problem, but it wasn't yet able to keep things in control in the tunnel. At 100 epochs, it still bonked in the tunnel, but not too badly. It was able to keep driving and finish the round. At 150 epochs, however, it was pretty perfect. It drives the corners well, doesn't hit any wall, and finishes 3 rounds without any problems. In fact, it's so consistent that rounds 2 and 3 were only 1/100th of a second apart. It was finally working. A machine learning model driving Mario Kart on a physical N64. Awesome. It even, with just 2 rounds of training data, manages to drive Calamari Desert. It leaves the road here and there, but is able to finish a full round. On other tracks, it doesn't perform so well yet. I guess more training on a wider variety of tracks is needed, but for Luigi's Raceway, it's pretty good. As always, you can find all the source code and so on linked in the description, and if you like this video, please subscribe. Also, if you have ideas for some other fun machine learning things, let me know in the comments. Thank you for watching and see you soon.